All right, welcome everyone. My name's Neil Fortner. I'm the chief architect at the HDF Group, and today I'm going to be talking about the new multi-dataset I/O feature that was released in 1.14. And I'm on the wrong focus. All right, so as a quick review, for an HDF5 file, most of the data, the column, data is going to be stored in datasets. At least that's the intention with HDF5 file format. And an HDF5 file can contain any number of data sets, and they can be used to describe, anything you want that can be described with numbers or bytes or whatever, different variables or conditions, etc. And the basic API for performing I/O on datasets, which is HRD read and HRD write, which has been around since the start, they only operate on one dataset at a time. So if you have 100 data sets in your file, you have to write to them one at a time. And each data set individually can also be broken up into multiple chunks, which are regularly spaced blocks of data within the data set. In a 2D data set, they're rectangles essentially. And IO, in addition to the chunks, you can also perform IO on only part of a data set, just a selection within a data set using, the HDF API. And so you don't have to read and write the entire data set at once. So we also support parallel MPI-based access to HDF5 files, where more than one process is accessing the file at once simultaneously. And we have a few different modes for this parallel data access. The first one, the most basic one, is independent, and that's basically where each process acts as if it's by itself. So each rank performs I/O independently, and there's no coordination. And the only difference with parallel versus non-parallel is we turn off some things, some caching and things, so that things stay consistent, because more than one process is accessing it at a time. And also, you can only do independent I/O on raw data and data sets. You can't do independent I/O on metadata or no writes. So the one advantage is that for independent parallel raw data I/O is that there's no time loss due to waiting for synchronization. So each process goes and does its thing, and then goes off and doesn't have to wait for other processes to finish their stuff. But because it's independent operation, means we can't, since in the library we don't have all the processes, we can't call MPI file set view because that's a collective operation that requires all the processes to call it. And since we can't call MPI file set view, we can't do non-contiguous IO on the file. So for each contiguous block in IO, we need to call MPI file read or write once. So you can imagine if you have a 2D data set and you select a column in C ordering, then you have to make a bunch of different low-level IO calls, and that can potentially be a big performance overhead. And so, and more generally, we're potentially losing performance because we're not giving MPI IO the full picture of the IO that is to be performed, and that means that the MPI IO can't be as smart as possible about how to perform that data, shuffling it to different servers and things like that, in coordination between the different ranks. And this is both due to the need for contiguous blocks because of the file set view issue, and because we're only giving MPIO information from a single rank. So here's sort of a graphical representation about what I'm talking about. So if you have this 2D data set that's broken up into 4 chunks, so it's a 10 by 24 data set. And so in this example, you have to make a file read write call for each each little row here in each chunk. So that means 1, 2, 3, 4, 5 in this chunk, 1, 2, 3, 4, 5 in this chunk, and so 20 calls total. So again, that, and obviously these data sets could be much larger. So that could be, if you're calling API file write in a loop, you could, add a lot of overhead there. So the next mode is called multi-chunk collective, and this is sort of like a low-level IO mode inside the MPI IO code in the HDF5 library. And so multi-chunk collective looks at each chunk individually, but this is a collective mode, so that all the processes have to call HDF write or HDF read at the same time. So the library knows that it has every process. So when it gets to each chunk, it can build a complicated MPI data type for each chunk. And this allows it to specify, an MPI data type is different from an HDF5 data type. An MPI data type describes the shape of the data. So in this case, it describes a non-contiguous data layout within each chunk. So in this case, the multi-chunk algorithm will construct an MPI data type and issue one MPI file read or write call or at all call for each chunk. So it's also worth mentioning that if collective IO doesn't work well on your system, you can still use this mode by specifying that it use independent low-level IO. So you'll use collective for coordination between processes, but then it'll fall back to independent when it actually calls MPI. And so this method gives more information to MPI than the independent method that I went over before. And it also, because it's operating on one chunk at a time, it also doesn't make huge MPI data types, but it also doesn't give as much information as the later methods we'll talk about. So here we'll go over the same example, same IO, but this time it's multi-chunk. So in this case, the library will go to chunk by chunk. So for the first chunk, it'll look at this. They'll build a MPI data type describing this layout. So in this case, an MPI, because it doesn't have the dimensionality, it'll just be three blocks, 3 times element size, then a whole, then another 3 elements, then a whole, and so on. And so it'll call MPI file read or write at all with every process for this chunk. Then it'll move on to the next chunk and it'll do the same thing. So it'll make four calls to MPI total. And the third, before we get to multi-data set, the third and most complicated parallel raw data IO method is called linked chunk collective. And this, what it does is it sort of builds on the multi-chunk, but instead of building an MPI data type for each chunk, it looks at all the chunks together and it builds a greater MPI data type, an uber MPI data type that contains information about all of the chunks in the data set that are involved in IO. And again, the underlying IO can be independent or collective, and this means that there's only a single MPI file read or write call per data set. And again, it gives a maximum amount of information to MPI possible for a single data set, given the legacy HID read and write APIs. I say legacy, but they're not deprecated or anything. We're keeping them around. And so again, back to the same example, if this is one data set, then MPI will build a data type for this chunk, then build a data type for this chunk, then build a data type for this chunk, then build a data type for this chunk. They'll create a greater data type out of these 4 data types, so that there's just a single MPI data type that describes all 4 selections in all 4 chunks. And then I'll call MPI file read or write once. All right, and so now finally we get to what the topic of this talk is multi-dataset IO, and this is sort of a logical continuation of the linked dataset. And it's basically it takes the idea of stitching the data types together further, where not only are you stitching the data types from the different chunks together, you're also stitching stitching together data types from all the chunks in all the data sets are involved in the IO. So in order to support this, we introduced 2 new APIs that allow you uh, to perform IO on more than one data set at a time. Because, very often, applications will have different data sets for different parts of the simulation that they might be running or something like that. And they might for checkpointing or visualization, they might want to access all of them at once. In fact, there are several applications that do that. It's pretty common, I think. And so right, with the previous API, it would have to call HID read or write for each of those data sets individually. So by adding the new APIs that allow you to operate on more than one data set at a time, it is convenient because it allows you to just make one call, and it'll also potentially allow higher performance. So again, it takes the link chunk concept further and allows a library to build a MPI data type that operates on all the data sets and all the chunks and all the selections within the larger IO. And this was released in HDF5 1.14. This is the API here. So we have HID read multi and HID write multi. So these are probably if you're familiar with the HDF5 API, these probably look familiar. They're basically the same as HID read and HID write, except we have this count parameter at the start here. And all of the other parameters, they're the same as in the single dataset APIs, except they're arrays now, with the only exception being the dataset transfer property list. There's only one dataset transfer property list for the entire operation, but all the others, they're arrays. So the count is the number of datasets, and then each element in each of these arrays sort of matches up to the matching element in all the other arrays. So you have n data sets, n memory types, and n memory spaces, etc. This is going to be a little shorter than the time allotted, but plenty of time for questions. All right, so I think there's more benchmarks, but this is sort of what I had sitting around. So here's a standalone benchmark. It's worth mentioning that, like the independent versus collective choice, it's not one method isn't always faster than the other. So this is just another method that in many cases will maybe faster, but it isn't always going to be faster. So this will kind of illustrate that. So here there's a standalone benchmark. The dotted lines are the single data set, and the solid lines are multi-data set. So this is sort of showing how the time needed to complete the operation scales with the number of data sets. And so the time is bad. So lower numbers are better. So with just looping over the number of data sets, for the write case on this machine, in collective IO, it scales very poorly. You can see it basically and takes well, I guess it's sort of, because it's 7 gigabytes per data set, so I guess it's kind of a constant bit rate. So you're not getting any benefit from adding more data sets. You can't get any more throughput. But when you but the read actually works pretty well in this case. And so when you switch to multi-data set, you'll see that it drops from at the high end from 600 to about like 40. So that's more than order of magnitude speed up for the write by enabling collective IO instead of just loop. So this is collective IO, and this is looped over the data, or this is, sorry, this is multi-data set collective, and this is single data set collective with in a loop. So you can see that for the write, it gives you a huge speed up, but for the read, it actually slows down. So again, at least above 64 data sets, it slows down. I don't know the reason for this. It's probably something to do with the underlying IO system. But again, it's worth experimenting with. It gives you another option to possibly greatly improve performance. And you can actually, if you kind of zoom in, that you can see that it's actually faster in the read for some lower numbers of data sets. And then just sort of a sanity check, we also ran it for independent and show that it's pretty much the same results, because which is as expected, because when there's independent IO, it doesn't build any of those data sets or anything. It just does one block at a time. Just calls HDF or MPI file write or read just one block at a time, and so it doesn't really matter whether you're doing multi-data set or single data set, because it all goes down to the same MPI operations at the bottom. But it does help to show that the multi-data set code path isn't giving us any huge overhead. So, and then this is I think this is essentially the same benchmark, but it's on a different system. And here we show that in the collective case that both read and write are improved. However, and also independent is more or less the same as expected. However, if you look at the scales, we'll see that on this machine, independent is much faster than collective. So this is a case where you would probably just want to use independent IO, and you could use the right multi APIs for convenience, but you would probably want to use independent low-level IO. And to go back to the previous slide, the time scales on this one are the same. So in this case, the collective multi-data set does give you a huge benefit over independent and over collective non-multi-data set, which is interestingly, collective non-multi-data set is the same speed as independent, at least for write. All right. And another benchmark that doesn't have a graph, but this was the real application CGNS, and this is sort of since it's not a synthetic benchmark, it's not as sort of tuned for showing the differences, and there's only it's only reducing 16 calls to 6 multi calls, so it's not expecting to see a huge difference, but we do see 6 to 10% improvement in file throughput by enabling multi-data set, which is not huge, but it's worthwhile. So now I'm going to talk about where this is supported. So for the write and read multi, all ranks need to pass the same list of data sets. We thought about, I actually tried to implement it without it, but it ended up being difficult, and it would have required more coordination between processes, and we figured it was best just to require the same list of data sets for now. All the data sets have to be in the same file, so there's no multi-file IO yet, and I'm not sure that would actually bias anything in terms of performance. And each data set can only be present once in the list, and again, this was something I tried to implement, but it ended up being very difficult because of how selections could sort of allowing the data sets to be present twice could make it very difficult to implement because of how selections could conflict inside the same chunk and things like that. The selection IO feature, which I'll talk more about in a few weeks. I'll come back and do one of these on selection IO, but it's fully supported by multi-data set. Selection IO is useful, particularly if you're trying to write a virtual file driver that is, similar to what we were talking about before. If you're trying to write a virtual file driver that's operating on more than just a single offset in length of bytes at a time, then selection IO will be beneficial. And so that feature it's out in a sort of experimental form right now in 1.14.0, but it's going to be productized in 1.14.1. And in order to get the simultaneous collective multi-dataset IO, so where the library will actually build the big data type and issue a single MPI call under the covers. These are the requirements. So obviously it needs to be set in collective mode, because independent is the default, and because we just because that was what we decided for HDF5. And you can't use compression right now. It's not implemented yet. Well, I mean, it'll work, but it'll fall back to one dataset at a time. And right now in 1.14.0, none of the datasets can use type conversion. That's sort of an existing limitation in HDF5 that's been around, since the beginning, is that there's no collective IO with type conversion, but it's worth mentioning that in 1.14.1, we're going to allow collective type conversion when you're using selection IO, with some other limitations, mostly involving memory, that I'll talk about in a few weeks. And all the datasets have to be contiguous or chunked. And again, otherwise the library will handle one dataset at a time. So current status and future work. Also all the vol's been updated in 1.14.0 to add the read multi and write multi. So if you have a vol connector and you haven't updated it for 1.14.0, you'll need to update it for those. We still support the multi-chunk and the independent IO pathways we talked about before, but the link chunk is now basically been superseded by multi-dataset. So if you are doing a multi-dataset IO, it's either going to be independent, multi-chunk, or multi-dataset. If there was demand for it, we could implement link chunk one dataset at a time. But right now, we're not sure that that's has a use case. And you could test it by, again, doing one data set at a time. And if any of the data sets, violate any of these conditions, then all of the data sets will fall back to multi-chunk. So it won't do like link chunk on all the data sets that support it, and then multi-chunk on the others. And again, we're currently implementing support for type conversion with collective IO, with or without multi-dataset, and it requires selection IO, and I'll cover it on a future episode. So does anyone have any questions? That was all I have for today.
Yeah, I have. Thank you, Neil. Even I'm listening to this maybe second time.
Right.
I'm lost because there are so many concepts, and I was wondering, just to clarify, for just one dataset IO, there are property functions that can modify and override algorithms how internal IO is performed, right?
Right.
Right. And I probably missed here, maybe you told, are they similar for multi-data sets or no?
I would have to check the specifics. I believe that it uses the same functions, and it just treats the multi-data set,
As chunk
linked data set, I guess, if you want to call it, is the same as linked chunk
is linked
before.
chunk. Okay. And do you remember if there is a document that describes all those internal modes and default behavior of the library? I remember there was a document, but I cannot find it.
There probably is, but I don't know off the top of my head where it is.
Okay, I will try to look around. I believe Mohammed wrote it, or Mohammed and Quincy, because
Mhm.
there are so many concepts here. It's hard to remember. And
Right.
yeah. Okay.
Yeah, there's a heuristic for when it switches between one and the between link chunk and multi-chunk. But I don't remember what it is exactly.
And there are APIs for other participants that allow you to retrieve what actually was performed by the library.
Yes, yes, there's the actual get actual IO mode.
And it will apply the same for multi-data set, right?
Right. So the get actual IO mode, it's a little weird. It returns it calls it an enum, but it's really a bit field because the enum values are different, single bits, and it will OR them together if more than one applies. So it's really a bit field, or bit flags parameter, and so it'll tell you, and that gets more important for multi-data set because, like, if you have contiguous and chunk data sets in your IO operation, it'll IO then the get actual IO mode will OR together the contiguous collective and the chunk collective flags. So I'll tell you sort of all the different IO modes that were performed.
It will be good to have documents that explains this all.
Right.
Okay, thank you. And there is a question from Joe in the chat.
Right.
Yeah,
In the
let
chat.
me read that just so that our recording is complete. He says, do you have a benchmark of reading and writing 1 million data sets of a small 1 megabyte data, i.e. the opposite case of what the benchmark slide showed? If not, what's your prediction? Will multi-data set IO benefit for this case as well or not?
I don't think we have that. I don't think we have that particular benchmark. I think that the ones with the slides are sort of the closest to that. I mean, it only goes up to 256 data sets. My prediction is that it would overwhelm, honestly, the MPI IO layer, but it really depends on the system. So I don't think the limit, I don't think it would be determined by HDF5's implementation is what I'm saying. It really depends on the system, but I would guess, and I'm not an expert in this by any means, is that it would overwhelm the MPI IO implementation if you tried to do that. But I could be wrong, because I guess if it's not as complicated selection in each data set, then it might not be too bad. It would be a very large data type, certainly. Yeah, I guess you'd have to try it, and it might not be, it wouldn't be that hard to try, but so yeah, it's definitely interesting. And if we have some time, I might try something like that. But it would be very system dependent. Elena?
Yes, so in sequential case, it will do one by one. It will not build anything that can, for example, build big IO and pull out all or allocate space and write to the space disk or read it back. Like with sieve buffer, I believe there was the sieve buffer that allowed you to modify when you have disjoint selections to read by bigger buffers instead of going element from element.
Right. So so when you're not using when you're not accessing the file in parallel, then if you're not using selection IO, then yeah, it'll do it one data set at a time. If you are using selection IO, then it will build up a selection or a list of selections across all the data sets, and it'll pass that to the file driver layer.
Okay, and how do I invoke selection IO?
Well, right, right in 114.0, there's an environment variable is the usual way to do it.
Okay.
But we're gonna be adding APIs
Okay, thank you.
in 114.1. And it's also the plan for 114.1 is we're actually going to enable selection IO automatically if we detect that the file driver can benefit from it. Are there any other questions? Let me see if I can see the chat. Yeah.
Nothing else in chat right now. Okay, so next week, so thank you, first of all, Neil, for subbing in for Alexander this week. And sounds like we'll have you again as a guest shortly. And then next week we have Scott. So we'll see everybody next week if there are no further questions. Right, thanks, everyone.
Great.
Bye-bye.
Thanks. Bye.
Thank you. Bye-bye.